Hello, and welcome to this application presentation on the paper Detecting Network Intrusions via Sampling, a Game Theoretic Approach. This paper was written by Murali Kodialam and TV Lakshman. It's being presented by Joey Lovato. The presentation outline is going to go as follows. We're going to first look at the background and then dive into the problem definition. We will then formulate the game, followed by solving it. And finally, we'll look at some improvements as well as some variants and extensions. First, let's look at the background. So a communication network is made up of nodes and links. So if someone at node A wants to send someone at node T a packet, the packet must be forwarded along some links and nodes between A and T. That's most likely how you're viewing this video right now. But not everybody in the network has good intentions. Some intruder may be trying to send a malicious packet from attack node A to target node T. However, there is an overarching service provider that can sample the network for these malicious packets. They can essentially send all these packets to some sort of central node and sample them to make sure that they're not malicious, therefore diverting the packet from the target node if it is malicious. So we can see that this is starting to become a game between the intruder and the service provider in the context and domain of the network. Next, let's define the problem. First, let's just do some quick mathematical notation definitions. So our network is going to be defined as a graph G, where we have a N is a set of nodes, and E is the set of unidirectional links. We're also going to have N number of nodes and M number of links in the network. And for any link E in the set of all links, it's going to have some capacity denoted by C and some traffic flow denoted by F. Given two nodes U and V, we're going to let P of UV represent the set of paths from U to V. We're also going to know that M of UV with W denotes the maximum flow between U and V, where W is the set of link capacities. There's also a min cut between U and V represented by CUV, which we'll talk about a little bit later. Next, let's look at the objectives and constraints. So for the first player, which is the intruder, we can say that the intruder has some knowledge about the network capacities and network topology to make this a little bit more difficult for the service provider. So using a mixed strategy, the intruder is trying to inject a packet along some path P in all the set of paths. The service provider also has knowledge of the network capacities and network topology because they control the network. And also using some sort of mixed strategy, they're going to be sampling some links in the network with a sampling budget constraint. So here we can see that the service provider is deciding to sample some links. And we can see on the right there we have a summation of all the sampling rates from across all the links. We're going to make sure that that's always less than or equal to the budget constraint B. So we're not going to sample more than that. We're also going to define PE as being the probability that a packet is being sampled on some link E. So that's just the total sampling rate divided by the total flow on that link. Next, let's look at the game formulation. So what is the intruder going to be doing? Well, the intruder is going to be trying to find a probability distribution Q over all the set of possible paths. So here we can see that V is going to be the set of all possible probability distributions such that for every path in P, if we apply Q to P, we're going to get 1. So basically there's a 100% chance that the intruder will send the malicious packet on one of the paths in P. The service provider is going to basically find a set of links that they're going to decide to sample. So we're going to have a probability vector P, which satisfies the sampling budget. So here we define U as all M vectors P, thus that we satisfy the sampling budget. And here we can see that PE times FE is just the sampling rate. So what's the payoff going to be? Well, the payoff is going to actually be the expected number of times that the malicious packet is detected as it goes from A to T. So let's see how that can be mathematically shown. So here we have the summation of all the paths, and for each of those paths, we're going to apply the intruder's probability distribution function. So we're basically going to see what's the probability that this path has been chosen by the intruder. Then for that path, we're going to sum all the probabilities along all those links that the service provider is sampling those. So this is going to give us some idea of the total probabilistic chance that the packet going from A to T is going to be sampled by the service provider. So here we can see that the intruder is trying to pick a distribution Q that's minimizing the maximum value of this payoff. But why are we doing this? Well, we can kind of use some intuition here that the intruder assumes that the service provider is trying to maximize the number of malicious packets being sampled. So they're going to essentially minimize this maximum value. In reflection, we can see that the service provider assumes that the intruder is trying to minimize the number of malicious packets being sampled. So they're trying to maximize this minimum value. The value of this game theta is actually going to be equivalent to the result of these equations, and this turns out to be a classic two-person zero-sum game with a min-max result, because however many packets the service provider is able to sample, that's not so many good packets that the malicious packet's going to have to be sampled from, and that's not so good for the intruder. Next, let's solve the game. So via some sophisticated optimization mathematics, i.e. dual variables on that last equation we saw, we actually find the solution of this game to be that theta is equal to the total sampling budget divided by the maximum flow from A to T. And with some intuition, this actually makes sense. We're essentially seeing what the probability is that a packet is going to be sampled as it travels from A to T. And that's essentially the total sampling budget divided by the maximum flow from A to T. So what does this say about the strategies? Well, essentially, the intruder is going to do something like this. They're first going to find the maximum flow from A to T, and then they're going to decompose that maximum flow onto all the paths that it could choose. And we're going to denote all those decompositions as M1 through ML. And note that if we sum all them together, we're just going to get the total maximum flow. And then we're actually going to choose or introduce the malicious packet along P sub I with probability of the decomposed maximum flow at I divided by the total flow. For the service provider, we're going to do something similar. So we are going to take the maximum flow, and we'll see in just a moment that we can actually do this with a minimum cut. And we're going to have all the edges on that minimum cut with flows F1 through FR. And we can see that if we add all those up, we're also going to get the maximum flow. And we're going to sample each link EI with the total budget constraint multiplied by the flow divided by the maximum flow. So what does this really mean? Well, first let's look at this interesting relationship between maximum flow and min cut. So if we look at this sample network where we're trying to go from A to T here, there's actually a minimum cut. And this minimum cut is basically a cut in which we segregate the graph into groups where A is in the other group and T is in the other group here. And we can see that this is a min cut because with this 7.5 plus 4.0 is actually going to be the minimum number here. So that means that this is the maximum flow from A to T. So for the intruder, we're going to introduce the malicious packet along three different paths here. using this decomposition of the maximum flow. So we can see these first two. So if we do 1, 2, 5, we can see that 7.5 of the flow has to go from 1 to 2. And then we can have 7 of that going from 2 to 5. So therefore we have the maximum flow of 7 there. So we're going to have 7 divided by the total maximum flow, 11.5. And then we still need to do that other 0.5 that came across that min cut there from 1 to 2. So that's going to be a probability of 0.5 over 11.5. Then we're going to introduce the malicious packet along 1, 3, 4, 5 with 4.0 divided by 11.5, which is the rest. So if you look at this and add them up, we can see we get a probability of 100% that we're going from A to T. Now we're going to look at what the service provider is going to do. So the service provider is just going to look at this minimum cut, which once again, the minimum cut can help us get to the maximum flow here. So we can actually just look at the minimum cut and look at how much flow across there is of the total maximum flow. So for example, the sample link 1, 2 has 7.5 flow of the total maximum flow, 11.5. So essentially going to multiply the sampling budget, which is 5 in this case. We're going to multiply that by the fraction 7.5 or 11.5. And then similarly, on the sample link 4, 5, we're going to see that we have the fraction 4, that's the flow of 4, with a total maximum flow of 11.5 still. So here we can see that those two fractions add up to 11.5, and we're just multiplying those by the budget constraint so that we distribute all the possible sampling we can do to this minimum cut, which is the maximum flow. From this, we can also show that the value of the game theta is 5 over 11.5, and intuitively this is basically saying that for every 11.5 malicious packets sent, 5 of them are going to be sampled by the service provider. It's actually not too bad. But with these optimal strategies set, is it possible to increase the value of the game? Next, let's look how we can do this with some improvements. So we can actually use routing to increase the value of the game. So the service provider can actually control the flow of the network, but of course we're going to be restrained by some demands. So here's an example with the demands on the left here. So these are source-destination pairs, and we are restrained by the fact that we need at least 5 capacity for 1 to 3, 3 capacity for 1 to 4, and so on. And then we also have the original source destination pair as well as the paths here with their flow. So this is the base network. So this is one of the algorithms that we could use. This is called the flow flushing algorithm. So if we use the flow flushing algorithm, we can see that we've changed the flows along here a little bit, and we've actually now increased the value of the game because our minimum cut is now 9.95. So that's better than before, and we've essentially increased the value of the game while still holding to our original strategies between the intruder and the service provider. The service provider is just getting a little bit more value of the game. Using the cut saturation algorithm, we can see that the minimum cut is now 7.0. So we have the value of the game now 5 over 7, which is even better. Finally, let's look at some variants and extensions. So far we've really just seen a single attack node and a single target node, but in the real world, the intruder is going to be a little bit more sophisticated. So we might have multiple attack nodes to a single target node, and maybe even multiple attack nodes to multiple target nodes. So the authors did a little bit of experiment on this, and their results are as follows. So here, as you can see, we have some attack nodes and some target nodes. And for each row, we have some where we have just one attack node, one target node. But we also have some where we have multiple attack nodes and multiple target nodes. So this is our extension. And here, we're actually going to be using the 3 different routing algorithms to increase the value of the game. F1 is the minimum highest utilized link, an algorithm we didn't see, but then we also have the flow flushing and the cut saturation. So I'd just like to note here that this table actually shows the value of the maximum flow, not the value of the game. So if we're assuming that the sampling budget is constant, we're actually going to be looking for the smallest value in this table, because that means that we're going to have the highest chances of detecting a malicious packet. So here we can see where we have attack node 7 and target node 11, and we're using cut saturation, we're actually getting a pretty decent chance. The quiz question for this presentation is going to be, which network operations can help formulate the strategies for the intruder and the service provider? A. Flow flushing algorithm. B. Min cut. C. Maximum flow. D. Both B and C. Thank you. If you have any questions, don't hesitate to contact me at jlovato@minds.edu.